June 23, 1944. North Atlantic, 15 degrees 16 minutes north, 39 degrees 55 minutes west. A Grumman TBF Avenger circled in darkness above, coordinates that should have been empty ocean. Below, invisible in the black water, submarine I-52 carried 2.2 tons of gold, strategic materials, and Japan's desperate hopes for German radar technology. The pilot dropped a cylindrical object no larger than a mailbox. It splashed into the Atlantic, transmitted a brief radio pulse, then began listening. 3 minutes later, the sonobuoys hydrophone detected propeller noise. The sound was unmistakable, a submarine running submerged at depth. The pilot armed a Mark 24 acoustic torpedo, nicknamed FIDO, and released it into the darkness. No periscope sighting, no visual contact. Just sound transmitted through water, relayed by radio to an aircraft, converted to targeting data, and delivered by a weapon that homed on engine noise. At 23:45 hours, the sonobuoy recorded an explosion. I-52 and her entire crew vanished. Tokyo received only silence. What Japanese Naval Command could not yet comprehend was that this kill represented something far more devastating than the loss of one submarine. The Pacific Ocean itself had become transparent. The seeds of this defeat had been planted years earlier, in decisions that seemed reasonable at the time, but would prove catastrophic. On December 8, 1941, as staff officers in Tokyo celebrated the Pearl Harbor attack, a memorandum on submarine employment lay buried in operational plans. The document outlined Japanese submarine doctrine, long-range reconnaissance, attrition warfare against capital ships, scouting for the combined fleet. Type B-1 submarines carried reconnaissance seaplanes with ranges exceeding 14,000 nautical miles. Type C submarines operated as fleet support vessels. The doctrine was clear and consistent with Japanese naval thinking developed over decades. Admiral Isoroku Yamamoto reviewed the plans with professional satisfaction. Japanese submarines would support decisive fleet actions. They would scout enemy dispositions. They would attrite American battleships before the climactic surface engagement. What the plans did not emphasize, what Japanese doctrine fundamentally misunderstood, was that this war would be decided by logistics, not battle line exchanges. The contrast was already apparent to those willing to see it. American war plans emphasized commerce destruction and maritime interdiction. German U-boats had nearly strangled Britain through unrestricted submarine warfare, but Japan allocated its submarine force to fleet support missions, not systematic attacks on American supply lines. The merchant ships, carrying fuel, ammunition, food, and replacement equipment across the Pacific, would operate relatively unmolested by Japanese submarines. This strategic decision made operational sense within Japanese naval theory. Decisive battle doctrine had governed planning since the Russo-Japanese War. Submarines existed to support the main fleet, not to conduct independent commerce campaigns. The assumption was reasonable wars were won through climactic naval battles, not by slowly strangling enemy logistics. The assumption was catastrophically wrong. By 1942, Japan fielded ocean-spanning submarines with capabilities matching or exceeding anything America possessed. Yet Japanese planners issued no program to mass-produce airborne radar, no crash development of shipborne radar systems, no emphasis on anti-submarine warfare technologies. The submarines themselves were superb. The doctrine guiding their employment was obsolete before the first shot was fired. While Japanese naval staff celebrated their doctrine's apparent validation 3,000 miles away, American shipyards were solving a very different problem. At the Electric Boat Company in Groton, Connecticut, a production foreman signed acceptance papers for hull section number 212 in early March 1942. A Bureau of Ships inspector stamped the documentation. The paperwork was mundane, bureaucratic, routine. What it represented was revolutionary standardized submarine production at industrial scale. Early American submarine operations had been hampered by torpedo defects and limited numbers. The Mark 14 torpedo, standard weapon for American submarines, suffered from multiple catastrophic failures. Magnetic exploders detonated prematurely. Contact exploders failed to fire. Depth-keeping mechanisms ran deeper than set. American submarine commanders fired torpedoes that ran under targets without exploding, struck targets without detonating, or detonated prematurely before reaching targets. The Bureau of Ordnance initially refused to believe the reports. Torpedoes had been tested extensively. The mechanisms were sound. Combat failures must reflect poor maintenance or operator error. It took months of accumulated evidence, systematic testing, and increasingly desperate pleas from submarine commanders before the Bureau acknowledged the problems. By the time fixes were implemented in mid-1943, American submarines had wasted thousands of torpedoes on attacks that should have been successful. But while torpedo problems persisted, American shipyards solved production challenges with remarkable efficiency. The Gato-class fleet submarine became the standard design. Electric Boat, Portsmouth Naval Shipyard, Mare Island, and Manitowoc Shipbuilding produced submarines using standardized components and streamlined construction methods. By war's end, America would launch approximately 288 fleet submarines compared to Japan's 174 total submarine force. The production advantage extended beyond numbers. American submarines integrated technologies as baseline equipment that Japanese boats never received. SJ surface search radar allowed detection of targets at night and in poor visibility. SD air warning radar provided early detection of approaching aircraft. Improved sonar systems, QGB and QHB models, offered detection ranges approaching several thousand yards. The electronics integration created capabilities Japanese submarines could not match. Rear Admiral Charles A. Lockwood, Commander Submarine Force Pacific, oversaw not just submarine operations, but systematic improvement of equipment, tactics, and training. When torpedo problems were finally acknowledged, Lockwood personally supervised testing and demanded fixes. When radar proved its value, he ensured every submarine received the latest equipment. When sonar performance improved, upgraded systems flowed to forward bases. The American approach emphasized standardization and scalability. Submarine production utilized interchangeable components, allowing rapid construction and simplified maintenance. Training pipelines produced qualified crews faster than Japan could replace losses. The logistics system delivered spare parts, torpedoes, fuel, and provisions to forward bases with clockwork regularity. In 1943 alone, American submarines sank more Japanese tonnage than Japan's entire pre-war annual merchant shipbuilding capacity. The numbers were staggering and strategically decisive. Japanese merchant marine losses exceeded construction rates from the war's first year. Oil tankers carrying fuel from the Dutch East Indies to Japan disappeared with increasing frequency. Troop transports sank before reaching threatened garrisons. Supply ships carrying food, ammunition, and equipment vanished without trace. Japanese submarine force achieved nothing comparable. In 1942, Japanese submarines sank 184 Allied ships, totaling roughly 900,000 tons. This represented significant tactical success, but paled compared to American and German submarine achievements. More critically, Japanese submarine doctrine never shifted towards systematic commerce warfare. Submarines continued supporting fleet operations, even as American logistics networks expanded across the Pacific with minimal interference. The reasons for Japan's technological stagnation became clear through examination of industrial facilities. By September 1943, engineers at Yokosuka Naval Arsenal worked under conditions that revealed the true state of Japanese naval development. Workshop lighting was dim to conserve electricity. A requisition ledger listed shortages that told a story more eloquent than any strategic assessment: copper wire, quartz crystals, precision components necessary for radar and sonar development. The entries documented industrial inadequacy, masked by tactical success. Japanese naval engineers understood electronics and acoustic detection principles as thoroughly as their American counterparts. They had examined captured American equipment. They had read technical journals. They knew what technologies were theoretically possible. What they lacked was industrial capacity to implement solutions at scale. Type 93 passive sonar, designated J19 inches, some references, represented Japan's primary underwater detection system. Effective detection range measured approximately 2,000 yards under favorable conditions. American QHB active sonar achieved detection ranges exceeding 10,000 yards. The 5-to-1 range advantage meant American submarines detected targets far beyond Japanese detection capabilities. Japanese engineers attempted to close the gap. Experimental hydrophone arrays showed promise in testing. Improved sonar designs incorporated lessons from German technology exchanges, but every prototype required components that factories could not supply in necessary quantities. Vacuum tubes required high-grade materials, increasingly unavailable. Wiring demanded copper that was prioritized for other applications. Quartz crystals for oscillators came from limited sources. The technical lag was documented systematically in post-war assessments. The United States Navy Technical Mission to Japan, conducted in 1946, examined captured Japanese equipment and interviewed surviving engineers. The mission's findings were devastating. Japanese electronics development lagged approximately 2 years behind American capabilities. This was not due to inferior theoretical knowledge, but to industrial bottlenecks and resource constraints that prevented implementing solutions. The contrast with American development was stark. While Japanese engineers struggled to source components for experimental sonar sets, American factories produced tens of thousands of sonar units, radar sets, and electronic systems. The industrial capacity difference manifested in deployed equipment. American submarines and anti-submarine forces operated with technology. Japanese forces could only prototype in laboratories. Japanese submarine operations adapted to these limitations through tactics emphasizing stealth and surprise. Boats operated at slow speeds to minimize detection. Attacks occurred at night, when American radar was less effective. Transit routes avoided areas with heavy Allied patrol presence. But these tactical adaptations could not overcome fundamental technological disadvantage. The Allies began deploying thousands of sonobuoys monthly. An underwater surveillance program Japan had no equivalent capability to match. Each sonobuoy represented a listening post that remained after aircraft departed. The cumulative effect created an acoustic surveillance network that detected submarine movements across vast ocean areas. Japanese submariners operated in an environment where the ocean itself had become an enemy intelligence asset. The technology that Japanese engineers could only prototype in laboratories was about to demonstrate its full potential in actual combat. On January 15, 1944, in the Atlantic approaches off Europe, hunter-killer groups centered on escort carriers like USS Bogue were perfecting techniques that would soon migrate to the Pacific theater. An aviation ordnanceman armed an ANCRT-1 sonobuoy with careful precision. The cylindrical device weighed 18 pounds and contained a hydrophone, radio transmitter, and battery pack. When dropped from an aircraft, it would float at the surface, while the hydrophone descended to 25 feet depth. The concept was revolutionary. Previously, aircraft could force submarines to dive through visual detection and attack, but maintaining contact after the submarine submerged was impossible. Aircraft circled the area hoping the submarine would surface, but contact was lost once the boat went deep. Sonobuoys changed this equation fundamentally. The pilot checked his receiver, tuned to the sonobuoy's transmission frequency. He had already dropped several buoys in a tactical pattern based on submarine movement predictions. Each buoy transmitted continuously, relaying underwater sounds to any aircraft within radio range. If the submarine moved, one buoy would detect increased propeller noise. The pilot could then drop additional buoys to track movement and maintain continuous contact. American hunter-killer groups combined escort carriers with destroyer escorts in coordinated anti-submarine operations. Aircraft provided aerial search and attack capability. Surface ships delivered depth charge and Hedgehog attacks. The integration of air and surface forces with sonobuoy technology created a lethal combination that German U-boats were experiencing in the Atlantic. The effectiveness statistics told the story clearly. In 1942, hunter-killer groups achieved approximately 1 U-boat kill for every 50 contacts. By 1944, the ratio improved to roughly 1 kill for every 3 contacts. This dramatic improvement reflected technological advantage: radar for surface detection, sonobuoys for underwater tracking, acoustic torpedoes for prosecution. The impact on submarine operations was profound and immediate. German U-boat commanders reported that maintaining stealth had become nearly impossible. Surfacing to recharge batteries meant almost certain radar detection. Running submerged meant sonobuoys could track movements. Attempts to evade pursuing aircraft often ran into additional aircraft vectored to the contact by sonobuoy reports. Composite squadrons VC-9 and VC-69, operating from escort carriers, compiled impressive records against U-boats using these technologies. Attack sequences documented in after-action reports showed the system's effectiveness. Radar detected surface submarine, aircraft approached for attack, submarine crash-dived. Sonobuoys deployed in pattern around dive position. Hydrophones detected submerged submarine movement. Additional aircraft vectored to contact. Acoustic torpedo or depth charges delivered. Contact lost, presumed kill. The Japanese submarine force would soon face identical technology in Pacific operations. Weekly sonobuoy drop counts reached thousands across all theaters by mid-1944. What began as experimental equipment in 1943 had become standard operational capability within 12 months. The underwater battlefield was becoming transparent through technology that Japan could not match or counter. The full integration of these systems would be demonstrated in an engagement that Tokyo never understood. Between June 23 and 24, 1944, in the North Atlantic, at coordinates already noted in our opening, I-52 represented Japan's desperate attempt to maintain technology exchange with Germany. Her cargo included raw materials, gold for payment, and strategic metals. The return cargo would include German radar designs, jet engine technology, and advanced weaponry. Previous technology exchange missions had delivered critical equipment, including examples of German sonar and fire control systems. American codebreakers reading Japanese naval communications through ultra decrypts knew I-52's route, schedule, and rendezvous coordinates. The submarine would meet German U-boat U-530 to receive a German liaison officer and updated routing instructions for the final approach to occupied France. American forces had ample time to position assets for interception. Aircraft from Composite Squadron VC-69, operating from escort carrier USS Bogue, located the rendezvous area. The transfer between I-52 and U-530 occurred on June 23. Lieutenant Commander Jesse D. Taylor's TBF Avenger arrived on station that evening as I-52 proceeded toward France alone. The engagement proceeded exactly as doctrine prescribed. Taylor detected I-52 on surface radar at approximately 2300 hours. The submarine crash-dived immediately, aware that aircraft presence meant danger. Taylor's crew deployed sonobuoys in a tactical pattern around the dive position. Within minutes, hydrophones detected propeller cavitation, the distinctive sound of a submarine's screws, creating tiny bubbles through water displacement. The Mark 24 acoustic torpedo, nicknamed FIDO, was designed specifically for this scenario. The weapon traveled at 12 knots, considerably slower than conventional torpedoes, but adequate for homing on submarine propeller noise. Effective range reached 4,000 yards. The torpedo required no visual contact, no periscope sighting, no surface target. It simply followed sound. Taylor released the FIDO at approximately 23:40 hours. The torpedo entered the water, activated its acoustic seeker, detected propeller noise, and began homing. I-52's crew had no warning. No visible wake approached their position. The submarine was not running silent. Depth and course changes generated noise that the acoustic seeker tracked easily. At 23:45 hours, multiple sonobuoys detected an explosion. The detonation signature was consistent with torpedo impact, followed by secondary explosions from the submarine's batteries or fuel. Surface debris would later confirm the kill, though the wreck would not be located until oceanographic surveys decades after the war. Tokyo headquarters received no distress call. I-52 simply disappeared. Her last message reported successful rendezvous with U-530 and continuation toward France. Then silence. Japanese naval staff assumed U-boat attack, mine strike, or mechanical failure. The truth that American forces had intercepted and destroyed I-52 using technology Japanese submariners had never encountered remained unknown. The I-52 sinking demonstrated the complete integration of signals intelligence, radar detection, sonobuoy tracking, and acoustic torpedo prosecution. Each element alone represented significant technological capability. Combined into a coordinated system, they created an anti-submarine warfare capability against which conventional submarine operations offered almost no defense. The ocean had become transparent to forces with sufficient technology and resources. This pattern would repeat with increasing frequency as American forces extended their technological dominance across the Pacific. By October 1944, operations in the Truck Mariana sea lanes showed how comprehensively the tactical situation had shifted. Night surface transit had once offered Japanese submarines relative safety. Darkness concealed submarines from visual detection. American patrol aircraft operated primarily during daylight. Running on the surface allowed faster transit speeds and battery recharging. Japanese submarine commanders considered night surface operations reasonably safe through mid-1944. That calculation changed when American forces deployed airborne radar and surface radar in numbers that created comprehensive coverage. ASV Mark II and Mark III airborne radar sets detected surfaced submarines at ranges exceeding 10 miles in good conditions. SJ surface radar equipped on American destroyers and destroyer escorts provided similar capabilities. Night no longer offered concealment. A destroyer escort, operating off Truk, detected radar contact at approximately 2200 hours. The contact showed characteristics consistent with a submarine's small radar cross-section: slow speed, erratic movement, suggesting attempts to evade detection. The destroyer escort's captain ordered general quarters and increased speed to intercept. The Japanese submarine, likely a Type B or C boat based on operational area, detected the approaching warship and crash dived. This was standard procedure when surprised by surface forces. Submarines possessed neither the speed nor armament to engage destroyers on the surface. Diving offered the only hope of escape. But diving merely changed the nature of the threat. The destroyer escort deployed Hedgehog, a forward-throwing anti-submarine mortar that lobbed 24 projectiles ahead of the attacking ship. Each projectile contained 35 pounds of Torpex explosive and detonated on contact with submarine hull. Unlike depth charges that had to explode near the submarine to cause damage, Hedgehog rounds killed through direct hits. Additional anti-submarine forces vectored to the contact. Aircraft arrived with searchlights and sonobuoys. The submarine's movements were tracked continuously through multiple detection systems. Escape became impossible once the surveillance net closed. The submarine was hunted methodically over several hours until sonar contact was lost and oil slicks appeared on the surface. This engagement pattern repeated across Pacific operating areas through late 1944 and into 1945. Japanese submarines attempting night surface transits faced radar detection. Boats running submerged faced sonar tracking. Attempts to hide on the bottom in shallow water meant remaining stationary while Allied forces maintained persistent presence above. Every option offered only variations of defeat against opponents with overwhelming technological advantage. Magnetic and acoustic mines deployed at critical straits and channels added another layer to the anti-submarine network. Mines forced predictable routing through areas where patrol forces concentrated. Japanese submarine commanders faced impossible choices: risk minefields on direct routes or accept longer transit times through supposedly safer but heavily patrolled waters. Monthly shipping statistics documented the cumulative impact. Japanese tanker arrivals from the Dutch East Indies declined steadily through 1944. In November 1944, Allied submarines recorded one of their highest monthly totals, for Japanese ships sunk over 250,000 tons. American submarines operated with near impunity, while Japanese submarines faced losses exceeding 60% of deployed force. The industrial paralysis gripping Japanese naval development became increasingly evident as the war progressed. By January 1945, the situation at Yokosuka Sonar Development Workshop reflected the broader collapse of Japan's technological response. A prototype hydrophone array sat on the workbench, incomplete and obsolete before installation. Requisition forms, stamped deferred, documented the inability to source even basic components. Strategic bombing had disrupted production networks. Raw material shortages affected every program. Transportation systems struggled to move components between facilities. Commander Kozosato examined the prototype with professional frustration. The design incorporated lessons from German GHG sonar systems shared through technology exchange programs. Theoretical performance would match or exceed early American sonar sets. But theory could not overcome material reality. The prototype required piezoelectric crystals manufactured to precise specifications. Japanese industry could no longer supply these components in necessary quantities. High-quality copper wire for electrical systems came from dwindling stockpiles as copper mining and refining capacity declined under Allied pressure. Vacuum tubes for electronic systems required materials and manufacturing precision that bombed factories could not consistently deliver. Even if components could be sourced, manufacturing capacity for assembly was increasingly limited. Skilled workers had been conscripted for military service or diverted to aircraft production. Facilities faced electrical power shortages as American submarine operations interdicted coal shipments. Precision machining required for sonar components depended on machine tools that were prioritized for aircraft engine manufacturing. Post-war interviews with surviving engineers documented the desperate situation. Commander Sato testified to American debriefers that by early 1945, his team had completed perhaps 3 experimental sonar sets. None achieved performance comparable to operational American systems. None entered series production or fleet deployment. The technical gap that existed in 1943 had widened to an unbridgeable chasm by 1945. The contrast with American production was devastating. While 3 experimental Japanese sonar sets sat incomplete in Yokosuka workshop, American factories shipped tens of thousands of sonobuoys to Pacific bases. American submarines received upgraded sonar systems as standard during overhaul periods. American anti-submarine forces deployed detection equipment that exceeded Japanese capabilities by orders of magnitude. German technology sharing, intended to close the gap, could not overcome fundamental industrial limitations. Even when German designs were received and understood, implementing them in Japanese production environment proved impossible. The bottleneck was not knowledge, but capacity, physical inability to manufacture components at scale with available resources. Japanese submarine tactics reverted to desperate measures reflecting technological inadequacy. Boats operated at extremely low speeds to minimize acoustic signature. Commanders avoided transmission of radio messages that could be detected through direction finding. Transit routes took circuitous paths through areas with supposedly lower Allied presence. None of these adaptations addressed the fundamental problem. Allied forces possessed detection capabilities against which traditional submarine stealth offered limited protection. The scale of American technological deployment became visible through logistics records. By March 1945, clerks at Pacific Fleet Logistics Office in Pearl Harbor tallied electronics shipments with bureaucratic precision. The ledger entries documented industrial achievement that dwarfed anything Japan could accomplish. Sonobuoys by the thousands. Radar modules for submarines, destroyers, aircraft. Spare hydrophones, replacement vacuum tubes, testing equipment, maintenance manuals. The logistics pipeline delivered technology as consumable supplies. American anti-submarine warfare had transitioned from equipment scarcity in 1942 to equipment abundance by 1945. Early war operations had suffered from inadequate detection equipment. Sonar sets were primitive. Radar was experimental. Acoustic torpedoes did not exist. By 1945, American forces operated with technological overmatch across every category. Distribution systems extended the electronics grid across Pacific operating areas. Sonobuoys deployed from Marianas bases could track Japanese submarine movements from Okinawa to Philippines. HF/DF direction finding stations triangulated radio transmissions to provide accurate submarine position estimates. Radar-equipped patrol aircraft maintained continuous coverage of critical sea lanes. The surveillance network achieved near-comprehensive coverage through systematic application of industrial production. Rear Admiral Lockwood's staff documented the correlation between electronic supply and operational success. As sonobuoy availability increased, submarine contact rates improved proportionally. As radar equipment reached more patrol aircraft, surfaced submarine detections increased sharply. As acoustic torpedoes became standard loadout, kill rates per contact approached historical highs. The ComSubPac bulletins distributed to submarine commanders included increasingly confident assessments. Japanese anti-submarine capabilities remained primitive. Japanese submarine operations showed declining effectiveness. Allied submarine operations achieved unprecedented success rates. The bulletins reflected reality. Technological superiority had translated to operational dominance. By March 1945, cumulative Japanese submarine losses exceeded 60% of the submarine force, with no prospect of replacement or technological counter. New submarine construction barely replaced losses and offered no capability improvements over existing designs. Meanwhile, American submarine construction continued delivering boats with latest equipment as baseline installation. The industrial disparity extended beyond submarines to entire naval and air forces. American shipyards produced escort carriers faster than Japan could sink merchant ships. American aircraft factories built planes at rates exceeding Japanese pilot training capacity. American logistics delivered supplies and equipment that kept every element of the war machine operating at peak effectiveness. Japanese industry struggled to maintain minimal production rates while under relentless strategic bombing. The culmination of American technological superiority would come in an operation that seemed impossible under conventional thinking. By June 1, 1945, Admiral Charles A. Lockwood examined an operations map at ComSubPac headquarters in Pearl Harbor. The Tsushima Strait was marked with minefield positions in grease pencil. The Sea of Japan represented Japan's last protected operating area, an inland sea theoretically secure behind mine barriers and coastal defenses. American forces had avoided operations there throughout the war, respecting the geographic protection minefields provided. Admiral Charles A. Lockwood examined the map with professional interest. 9 American submarines would attempt entry using FM mine-detecting sonar designated QLA. Success would demonstrate that geographic barriers could be overcome through technology. Failure would prove that some defensive advantages remained absolute, even against technological superiority. The plan designated Operation Barney in honor of Captain Lockwood's mother-in-law, though operational security classified the mission details under strict protocols. 9 submarines under Captain Earl T. Heidman's command, nicknamed Heidman's Hellcats, would penetrate the strait, navigating through minefields, using QLA frequency-modulated sonar that could distinguish mines from seabed clutter. The technology was remarkable and untested in actual minefield penetration. QLA sonar transmitted frequency-modulated pulses that reflected differently from mines versus rocks or bottom features. The operator could identify mine shapes through distinctive return signals. Navigation required maintaining precise depth, following exact courses, and monitoring sonar returns with absolute concentration. Any error meant striking a mine with catastrophic results. Japanese defensive planning assumed minefields provided absolute protection. The Tsushima Strait minefields had been laid systematically, creating barriers that conventional navigation could not penetrate without triggering explosions. No submarine could reasonably expect to transit through fields that dense without catastrophic losses. The assumption was sound, based on available technology. The assumption did not account for American electronics development that had produced mine-discriminating sonar. The QLA equipment represented another technological solution to what appeared to be an insurmountable defensive advantage. If the technology worked as designed, geographic barriers that protected Japanese home waters would become merely another challenge that American innovation had overcome. Success depended on tolerances measured in feet. Mines suspended at specific depths required submarines to pass beneath them. The clearance between submarine sail and mine mooring cables might be only inches. Bottom features, wrecks, and mine anchors cluttered the sonar picture. Operators needed perfect concentration to distinguish mines from background clutter while navigating at periscope depth through potentially lethal waters. The execution exceeded even optimistic expectations. Beginning June 9th and continuing through June 26, 1945, 9 American submarines penetrated Tsushima Strait and operated freely in the Sea of Japan. The transit required approximately 12 hours of maximum concentration for each boat. Sonar operators tracked mines continuously. Commanding officers maintained precise depth and course. Every crew member understood that contact with a single mine meant immediate death. All 9 submarines transited successfully. Not one boat struck a mine. The mine-discriminating sonar worked exactly as designed. Japanese minefields that had protected home waters throughout the war had been rendered obsolete by technology Japanese forces did not possess and could not counter. Once inside the Sea of Japan, American submarines operated against Japanese shipping with devastating effectiveness. Targets were abundant coastal freighters, small warships, auxiliary vessels that had operated with relative security in supposedly protected waters. Japanese anti-submarine forces proved completely inadequate. Coastal patrol craft lacked modern sonar. Land-based aircraft had limited anti-submarine capabilities. The submarines could surface at night to recharge batteries with minimal risk. Over 17 days, the 9 submarines sank 28 Japanese ships, totaling approximately 70,000 tons. American losses, 0 submarines. The operation demonstrated complete technological dominance. Barriers that appeared absolute had been penetrated through American engineering. Japanese vessels operating in supposedly safe waters were destroyed with impunity. Japanese defenses proved incapable of detecting or engaging submarines operating in Japan's home waters. Commanding officers' patrol reports documented the targets and engagements methodically. QLA-guided transits were described in technical detail for future operations. Night surface attacks, using SJ radar targeting, followed standard procedures. Coordinated wolfpack tactics allowed submarines to share contact information and overwhelm defensive responses. Every aspect demonstrated mature operational capability against opponents unable to mount effective resistance. Japanese coastal defense logs recorded ships overdue with increasing frequency. Investigation revealed no wreckage, no distress calls, no survivors. Ships simply vanished between ports. The coastal shipping network that sustained Japanese industry and population faced systematic destruction from forces that appeared and disappeared without warning. The psychological impact on Japanese naval command was severe. The Sea of Japan had been considered secure. Mine barriers had protected home waters throughout 4 years of war. Now, American submarines operated there freely, sinking ships, conducting reconnaissance, demonstrating absolute mastery of underwater warfare. The barrier held until American electronics redefined what constituted a barrier. Meanwhile, Japan's most ambitious submarine program remained unable to execute its intended mission. Between late July and the August 30th surrender, the massive I-400 class submarine carriers at Kure Naval Arsenal represented enormous investment with zero combat return. The I-400 class boats, displacing approximately 6,500 tons submerged, measuring roughly 400 feet in length, and carrying 3 AGM-6A Seiran aircraft in watertight deck hangars, had consumed resources Japan could not afford. Each submarine cost enormous resources to build and required large trained crews to operate. The concept emphasized surprise air power projection. Submarines would approach enemy targets submerged and undetected. Aircraft would be prepared for launch while the submarine surfaced briefly. Seiran bombers would attack targets hundreds of miles inland, then ditch near the submarine for crew recovery. The tactical concept assumed American radar networks could not detect submarine launch operations, or that surprise would compensate for detection. The assumption was catastrophically wrong. By mid-1945, American radar coverage approached comprehensive levels. Any surfaced submarine faced immediate detection. Launch operations requiring significant time on the surface meant certain interception. The massive I-400 class boats were visible to radar at ranges exceeding 20 miles when surfaced. Aircraft launch procedures required precision and time, neither available under conditions where American aircraft would arrive within minutes of surfaced detection. I-400 and I-401 conducted training operations, but never launched combat missions. The vulnerability during launch operations made employment tactically unfeasible. Surface briefly, and American patrol aircraft appeared. Remain surfaced for launch preparation, and interception became certain. The submarines became liability rather than asset. Enormous resources invested in weapons that could not be used effectively. When Japan surrendered on August 15, 1945, I-400 and I-401 remained operational, but had never fired a shot in anger. Deck hangars remained unopened during potential combat operations. Aircraft maintenance logs showed training flights only. The submarines surrendered to American forces, who examined them with professional interest, mixed with recognition that size and novelty offered no advantage when detection technology rendered stealth impossible. American boarding parties documented the submarines thoroughly. The engineering was impressive: watertight aircraft hangars, catapult systems, specialized equipment throughout. The concept was innovative. Submarine aircraft carriers represented unique capability, but the execution encountered reality. In a surveilled ocean, size and surface operations meant vulnerability that negated any offensive capability. The I-400 class represented investment of resources Japan could not afford. Each submarine consumed steel, equipment, and skilled labor that might have produced multiple conventional submarines. The aircraft required specialized design, manufacturing, and maintenance. The operational concept required conditions that no longer existed by the time the submarines entered service. The world's largest submarines proved least usable in the most monitored maritime environment. The full accounting of the submarine war came quickly after surrender. By mid-September 1945, Allied intelligence clerks in Tokyo compiled ledgers documenting submarine operations throughout the Pacific War. The numbers told a story of overwhelming American technological and operational superiority. Japanese submarines numbered 174 boats total. American submarines sank approximately 128 Japanese submarines, roughly 74% of the force. American submarine losses totaled 52 boats, approximately 18% of deployed submarines. The offensive effectiveness comparison was even more lopsided. American submarines sank 1,314 Japanese ships, totaling 5.3 million tons. Japanese submarines sank 184 Allied vessels, totaling roughly 900,000 tons. The 6-to-1 tonnage advantage reflected fundamental differences in doctrine, technology, and operational execution. The statistics quantified what combat experience had demonstrated. Japanese submarine force achieved tactical successes but strategic failure. Individual boats occasionally sank important targets. Specific operations showed skill and courage, but aggregate results showed systematic defeat through technological disadvantage and doctrinal inflexibility. American submarines operated with comprehensive intelligence support, advanced electronics, reliable torpedoes after mid-1943, excellent logistics, and tactical doctrine emphasizing commerce warfare. Japanese submarines operated with declining intelligence, quality, primitive electronics, doctrine emphasizing fleet support over commerce, warfare, and logistics that deteriorated throughout the war. The United States Navy technical mission to Japan documented the technology gap systematically in 1946 reports. Japanese sonar lagged approximately 2 years behind American equivalents. Japanese radar development remained primitive through war's end. Japanese anti-submarine warfare capabilities never approached American standards. The findings concluded that Japanese submarine force was defeated by systematic technological inferiority, combined with doctrine ill-suited to Pacific War realities. Allied correlation studies linked American electronics delivery schedules with Japanese submarine loss rates. As radar deployment increased, Japanese submarine surface operations became increasingly hazardous. As sonobuoy production ramped up, Japanese submarine movements became trackable. As acoustic torpedo inventory grew, Japanese submarine losses per contact increased. The defeat lines graphed aligned directly with American technology deployment timelines. The testimony of senior Japanese officers provided the human perspective on these statistics. In October 1945, Rear Admiral Shigeyasu Nishiura sat in a Yokosuka debriefing facility, answering questions from American intelligence officers through an interpreter. His testimony would be recorded for technical and historical purposes, first-hand account from senior Japanese naval officer about submarine operations and technology. The admiral's statement captured the essential truth Japanese submariners had learned through bitter experience. By 1945, the ocean was no longer ours. It listened to us, and it spoke to our enemy. The ocean had become weaponized through technology that detected, tracked, and targeted submarines with efficiency that rendered traditional stealth obsolete. American debriefers requested clarification. What specific technologies most affected Japanese operations? The admiral's response covered familiar ground. Radar meant surface operations became suicidal. Sonar meant submerged operations could be tracked. Sonobuoys meant aircraft could maintain contact after submarines dived. Acoustic torpedoes meant weapons could home on submarine signatures without requiring visual contact. Direction finding meant radio transmissions revealed locations. Mine-detecting sonar meant geographic barriers could be penetrated. The cumulative effect created operational environment where Japanese submarines could not effectively operate. Every action generated signatures American forces could detect. Every defensive measure faced technological countermeasure. Traditional submarine advantages, stealth, surprise, concealment, became increasingly ineffective against surveillance systems that covered vast ocean areas. The synthesis represented systematic application of American technological development, industrial production, and operational doctrine. Individual technologies like radar or sonar provided significant advantages. Integrated into comprehensive system covering detection, tracking, and prosecution, they created anti-submarine warfare capability that Japanese forces could not counter with available resources. Post-war submarine design incorporated the lessons systematically. Quieting became paramount. Reduce acoustic signatures through improved machinery mounting, sound dampening materials, and refined hull forms. Anechoic coatings absorbed sonar pulses rather than reflecting them. Snorkels allowed diesel submarines to run engines while submerged, reducing surface exposure. Air-independent propulsion systems eventually allowed submarines to remain submerged for weeks. The future belonged to submarines designed around silence as primary survival characteristic. The contrast between Japanese and American approaches defined the outcome. Japan trusted traditional submarine capabilities, endurance, range, skilled crews. The United States weaponized detection through industrial-scale production of electronics that made endurance and range irrelevant when submarines could be found, tracked, and destroyed regardless of ocean location. In warfare decided by industrial capacity applied through technological innovation, the ocean itself became an American ally. Japanese submarines could not hide in an environment where sound, electromagnetic radiation, and thermal signatures betrayed presence to sensors deployed in overwhelming numbers. The Pacific War's submarine campaign demonstrated that technological overmatch, combined with industrial production, created victory despite tactical excellence or operational skill from the losing side. The final assessment from multiple sources: Allied intelligence, Japanese post-war testimony, historical analysis, reached identical conclusions. Japanese submarine force was defeated through systematic technological disadvantage that Japanese industry could not address given resource constraints and strategic situation. Individual Japanese submarines and crews demonstrated skill and courage. The submarine force, as strategic instrument, failed to achieve meaningful results against American logistics networks while suffering unsustainable losses. The lessons influenced naval planning for decades. Detection capability determined submarine effectiveness in modern warfare. Industrial capacity to produce detection and counter-detection systems in quantity decided campaigns. Operational doctrine alone could not overcome systematic technological disadvantage. These principles shaped Cold War submarine development, where acoustic quieting and detection technology competed in continuous technological spiral. The story of Japanese submarines in World War II ultimately represents clash between different approaches to naval warfare. Japan emphasized individual vessel quality, crew training, and tactical excellence within traditional operational frameworks. America emphasized technological development, industrial-scale production, and systematic application of advantages. When these philosophies collided in Pacific theater, technology and industry proved decisive. The ocean that once protected Japanese submarine operations became hostile environment, monitored by thousands of sensors, surveilled by countless aircraft, and patrolled by anti-submarine forces equipped with overwhelming technological advantages. Japanese submariners recognized reality. By 1945, they operated in ocean that belonged to their enemy, not through courage or skill, but through systematic application of science and industry to the problem of submarine detection. If you value fact-based military history, examining how industrial capacity and technological innovation shaped World War II outcomes, consider exploring additional content, examining other decisive campaigns where material advantage determined strategic results, despite tactical skill from defeated forces.